Can you hear me? Yeah. So good afternoon, everybody. I welcome you to a somewhat special session in this networking conference. It is special for two reasons. First, it is on Semantic Web, and Semantic Web is a little bit off what we have on regular protocol encodings, where we have the semantic hardly encoded. This is so more to the application layer. And the second speciality is that we have a speaker from abroad here. We are very happy to welcome Chris Basler. Hello, can you hear me?
Hi.
Hello.
Can hear you very well. Good afternoon.
So, we will be our last speaker in this session. We will start with a topic on multilingual management of websites, which is presented by Professor Olof Palme. Jakob Palme is from the University of Stockholm, and he has many years of experience in content management and high-level content applications. So, the floor is yours.
What you see here is the somewhat simplified version of the home page of our website. And you can see the web address at the top if you want to connect to it. It's a website which contains 800 informational pages. In almost all of them have been translated to 3 languages, and some of them have been translated to additionally 3 other languages. So in total we have information available in 6 languages at present. If any of you come from another language region and wants to make a version of this website for your language, you are welcome to do it. It will take about 1 person year of effort, and we can't pay you for it because we don't have any money. When we developed this website, it was done with European Union funding, but that funding has stopped for more than a year, almost a year ago. Our website has 2 main ways of finding an answer. Either you can type your question here in the question field, or you can click on one of the menu categories, and then you can use the menus to get around to all the pages. And when you type something here in the question field, this is not an ordinary search engine. It's a natural language question answering system which gives better results. I'll show here a little about how it works. The main principle of the natural language question answering system is that you have to produce, for every page, you have to produce a number of templates. And each of these templates is kind of standard, the kind of sentence you expect people to do. For example, for one of our pages, the template says that the sentence, the question, must contain any synonym of must or need or help, and any synonym of doctor or psychologist or expert. So, for example, must I get help from a doctor to stop smoking? In that sense, must I get help from a doctor to stop smoking? That question will match. Help will match that part, and doctor will match that. Do I need a psychologist? Will also match. Is expert help necessary? Will also match, because expert will match that, and help will match that. So any kind of question which contains any of these words and any of these words will match. And you can have many different templates if you want to for every answer in the database. And this is here is the actual language we are using for specifying these templates, but this is just a more complex way of saying the same thing I showed in the last picture. Here is a comparison of the results based on a random sample of actual real questions asked by our users. And we compared our own system, Quick Ask, and 90% of all the questions got good result. Then we tested Google by you writing site : followed by the name of our domain. So we used Google, but restricted to only searching on our website. 68% success. We also tested SiteSeeker in Swedish. It's a search engine which has some knowledge about the Swedish language. It got 72%. So you can see that Quick Ask got much better results than the other search engines. The disadvantage with doing it in this way, of course, is that you have to produce these template sentences for all the content in your database, and that's quite a lot of work. But the advantage is that you will be much better able to answer questions from people. Very important in managing a website like this is to scan the log files of questions people have actually asked. If someone has asked a question where our system did not produce a good answer, we have to find out why. Was it because we didn't have an answer? Then we ask our medical expert to write an answer. Was it because we had an answer but our system could not find it? Then we have to modify the templates so that the next time someone asks the same question, the person will get a good answer. This is quite important. Before we started doing this stepwise refinement, we missed about 15% of all questions. After doing this stepwise refinement work for 1 year, we missed only about 10%. So the number of missed questions got down from 15% to 10% after doing this 1 year, about half an hour every day. I worked on this stepwise refinement. So here are some examples of stepwise refinement. Someone wrote seeing things as a question, and we didn't have any answer. And then we had actually an answer about hallucinations and causes of it. So it was just that we didn't have the right template. So we changed the template for this already existing answer. And here are some other examples which also show how cases where the system originally did not find the right answers, but by changing 2D templates, we could make it find the right answer. This is very important. If anyone wants to have a good website, which makes it easy for people to find information on the website, you have to do this manual work of twiddling with the website to make it better and better stepwise by looking at the log files. This is absolutely essential. Some people believe that you can have an automatic search engine. You just look for the words and produce a list of all pages containing certain words or word combinations. That does not work, at least not very well. And all of us know that most websites on the web have very bad internal search engines because they have not gone into this effort of producing good structure of the database with this kind of classification. As here is what I said before, that after about 1 year of work of including it, we got down the number of missed questions, the questions not well answered, from 15% to 10% by this stepwise refinement. This is absolutely essential if you want to have a good website, that you have to do this kind of stepwise refinement. We also had a workflow system because if you have a website with content in several different languages, then there are often different people involved. First, we have the original author who wrote something. It goes to a translator, and when the translator has translated it, the original author can approve it. Also, we had the principle that every informational text written by one of our medical experts should be approved by another of our medical experts. There were always a second medical expert in another country who approved the text, and that also is a kind of workflow. So this kind of workflow is very important. And something we learned about how to implement workflow system is that it should be easy to check the status of every item in various stages in the workflow. It should be easy to diverge from the normal workflow when needed. And so the workflow is not a stepwise flow from step 1, 2, 3, 4, always in the same direction. Sometimes you want to go back, sometimes you want to skip a step. And the system must support that. It's very important also that you have something which reminds people of what they should do, something which often is known under the term news control. News control tells you what is new for you, what you should do about. So if an original author has written something and the translator should translate it, then the news control will provide a list to the translator the next time the translator connects, saying that this is what you should translate. We also have something called cross-lingual question answering. As I said before, the natural language question answering system we are using is based on templates. You have to develop several different template sentences for every answer. If you want, you can regard these templates as a kind of mini ontology around this answer. We could also have been used the Semantic Web, which also is a kind of ontology, but we have not done it yet. We will probably do it in the future, put all our text into the Semantic Web. Anyway, this, either if you put it into the Semantic Web or if you produce the templates the way we have done it, this is work which has to be done and which takes some time. And when we do this stepwise refinement, when we modify the templates, enhance them with new words and phrases so that you can cover new kind of questions, then these changes should, of course, migrate to all other languages. And this is not so easy. And one solution to this problem is shown. This figure shows how it could work in Italian, but we are doing the same for all languages except English. The question is put in, for example, Italian. We translate the question using the Systran machine translation engine from Italian to English. Then we put the translated question to the English natural language question answering system. It will then return a number of English FAQs. Then we find the corresponding Italian FAQs. And then we return the Italian FAQs. If we have an Italian natural language question answering database, we also put a question to that database. And then we merge the results of the Italian search and the English search are merged into a merged list of answers. If one of the answers had not been translated to Italian, was only available in English, then this merged list will contain the English text. But for every answer which has been translated to English, the merged list will contain the Italian answer. Even if you have done the searching using English, you will still show the Italian text to the person who is asking something. So now you may wonder, how good is this? Don't you have to have any Italian question answering at all? Can you do everything by doing a translation, which of course would be the ideal situation? And we have made some tests to find out how well it works to go this way instead of this route. Because this route would mean that you would only have to have one single natural language question answering, and also it would mean that when you do stepwise refinement, the refinement will automatically migrate to all languages, since all languages will go through English. You only have to change the English templates, and then this will work for all other languages. So we have tested how well does it work. And we found that using Systran as it is, the quality going this way was about 70% of the quality going this way. So it was not at all as good. However, if you equip Systran with a custom-made dictionary which contains the right words for our application area, then you can get almost as good this way as this way. To explain what I mean, I'll give an example. Take the English word body. It has two main meanings. One meaning is the main part of a document, and the other meaning is the body of a living being. And of course, since our website is a medical website, the body should be translated into the meaning of body of a living being. However, Systran by default translates body with the meaning main part of a document, because Systran is optimized for Office documents, and in Office documents, body more often means main part of a document. So in order to get this to work well, you have to equip Systran with additional dictionaries. This is not something we have not yet done, but this is something we hope to do in the future. But if you do that, if you give Systran dictionaries suitable for this area, then this way will give almost as good answers as this way. If you look at a website like our website, there is a lot of structure in the website. By structure, I mean, for example, the subject is, if you have a database, on a home page you can push on the link to Phobias, and then you get to a sub-page that contains links to different aspects of Phobias. Sometimes you can click on one more link to get to another sub-page if you have many answers in one area. And so, in that way, this subject tree area, like Yahoo database, is one important way of finding answer information in our database. Then internal links. If someone has found one answer, then this answer will often at the bottom of it contain links to other answers. And these links between one answer and other answers is also structure. And then if we had been using the semantic web, then the semantic web would also have been structure. With the natural language question answering system, the templates we produce for the natural question answering system is also kind of structure. So these are three examples: structure as subject trees, structures by links between pages, structures for the natural language question answering system. And this picture shows one example. In this picture I show the example of a subject tree. The subject tree begins with a number of topics, and then you have subtopics. You can go several levels. So this is one of the structures. We have several different. This is not the only structure. It's one possible structure, and we have several different ways of structure. We also have the natural language structuring, and we have the links between pages. But this is one structure. But what is important here is that this structure is mainly language independent. That I have written depression as the label of this node does not mean that this is language dependent, because there is a word in every language for depression, even if it's different in different words. But the structure, the logical structure here, is independent of language. However, when you come to the leaves in this text, in this structure, then when you have shown them to actual users, then you have to show them in the right language. So all the structure is language independent, but the text you show to the user is language dependent. And this is very important when you are managing a multilingual database, because you want to be able to change the database. And when you change the database, the change will automatically migrate to all the different languages. You don't have to redo the same change in the structure. And by keeping the structure language independent and only having the text labels on the items in the structure language dependent, this means that you can change the structure, and you may not have to change anything at all in the different languages. Or if you are changing the structure so that you are adding a new node in the structure, you have to translate the name of this node to the new languages, but nothing more than that. And this is very important for managing such a website. So if you are going to manage a website which contains the same information in many languages, I very strongly urge you to devise a content management system which is based on this idea that the structure is language independent and only the labels on the names is language dependent. So a summary of what I'm trying to tell you here is you should separate structure and translatable text. Structure has to be semantically defined, and the logics of semantics is the same in all languages, even if the text you put on the different items is different in different languages. Very important that you have support for stepwise refinement. By having support for stepwise refinement, you can improve the quality of the database by looking at the logs of how people are using it. And that's very important. Every good website are doing a stepwise refinement, otherwise they wouldn't be good. It's good to have an intelligent natural language question answering system like the one we are using, or another way, but just ordinary plain so-called free text search engines are not good. You have to do work to make question answering good, whatever tool you are using use for that. And you should support user-defined workflows where you can in a simple way check the status, and you can easily remind people of tasks to do, and which allow you to diverge from the normal flow. You don't always have to go in the same order. Here is a rather interesting picture. This picture shows statistics on how people come to use and leave our website. 72% of all people who come to our website come from search engines, most of them from Google. So using Google or another search engine, they come to one of our pages. They don't come to our home page. They come to one of our informational pages. After then we have another 28% who come in other ways than from search engines. This is people who have bookmarked our website or links where someone has put a link in his web page to our web page, and then people come. So most of them come from Google, but some come from links. And in both cases, people usually don't come to our home page. They come to one of our 800 pages, depending on which question you put to Google. For example, if you ask Google the question, tell me about gastric banding. You probably don't know what gastric banding is, but it's a medical method of treating obesity by changing, tying a band around the stomach so the stomach can't contain as much information. You can't eat as much as before. And if you ask that question to Google, you will probably, at least the last time I checked it, you'll get one of our pages as the first item you get from Google. Why was our page first for gastric banding in Google? Well, all the other pages of gastric banding in Google are pages put up by different medical clinics who want to sell you this kind of surgery. And our page was an objective page. We discussed the merits and dismerits. And Google is very good at finding out which pages are good. So Google found out that we had the best page on gastric banding, so then they go to that page. After viewing one page, people will either use our natural language question answering system to go to a new page. 12% of everyone will do that. 61% will click on a link, and 27% will exit. This means that on average, a visitor to our website will see about 3 pages. If you look at this figure, one thing which is rather interesting is that of all the times when someone sees a page in our websites, lots of them are because they are using Google. Lots of them are because people are clicking on links. Rather few of them, only 12%, are because people are using the natural language question answering system. Why is that? Well, my guess is that people are experienced that websites almost always have very bad search engines. So they don't expect that our search engine will be better than any other web search engine. And that's why they don't even try to use our search engine. One thing which is rather interesting about this figure is that if you want to help people find the relevant information, it's much more important to help Google direct them to the right page than it is to make quick ask, have them to find things. And also, it's much more important to provide a good structure of links between the pages than our natural language question answering system. This is rather surprising, and we didn't expect this. But now we know, if you want to help people, the links within the pages and between the pages are very, very important. And search engine optimization for Google is very, very important. And the natural language question answering system is not as important as we believe. Thank you.
Thank you very much. Are there questions? No questions here? Then I have a question. You showed that you put the medical terms in a taxonomy, in a hierarchical structure of relations, and you were discussing on language templates you're using. Question is, have you thought of, I mean, this is, I believe, what some people in the semantic search do, have you thought of extending your taxonomy by connecting it to a language-related ontology of synonyms and related terms?
To some extent, we have done that. We have, as part of the natural language question answering system, we have a synonym list. But this is a very special synonym list. It's the definition of synonym in our synonym list is very different. For example, in our synonym list, violence and sexual abuse are synonyms. Because people who ask a question about sexual abuse and people who ask a question about violence mostly want to find the same page. So our synonym list regards the idea of synonym rather widely. But if we have such a synonym list as part of the natural language question answering system, and that synonym list is very important, and we have translated it to several languages.
Are there more questions? You have a question? No, no. Okay.
I was pointing.
Oh, okay. You're pointing. So then let's thank the speaker again. Our next speaker also comes from Sweden. It is Roland Hedberg from, I can't pronounce it, Umeå University of Sweden. And he is concerned with a more general problem of delivering and distributing information along a university system, by, I believe, keeping the semantics of it.
Okay. So,
This is yours, isn't it?
yeah, it is, right? Well, good, great. So, do you hear me? Okay, great. Thanks for coming, I would say. Okay. I don't know why I ended up in this session, because what I'm going to talk about hasn't a lot to do anyway with the semantic web. I use some functionality that comes from the semantic web and might possibly do more of that in the future. I don't know. Anyway, this project started. I'm also have to apologize. There are a couple of spelling errors here. Actually, I found them when I sort of went through the presentation here just before, but I wasn't able to change that. So please disregard those. This isn't the only one. There are two more, I think. You don't get any points for spotting them, though. Okay. So this is the background. Within any organization, you have lots of things happening. And someone would be, well, pleased if they were to know that those things happen. And in some cases, you really have to have someone know that those things happen. And it could be almost anything. Like someone gets employed, someone is fired, a library buys a book, subscribes to a journal, someone starts sending a video stream, and which is very common at university. A number of departments fuse into one, or one department sort of gets to be a couple of departments. I mean, the organization is changing all the time. And like if it's a university, you have tests. The student takes tests, so the information is registered somewhere. But this is just to show that the disparity, I mean, the volume of events that happen as a university. I mean, university isn't any special. This goes for any organization. But since I'm working for the university, I'm sort of looking at what's happening at the university. So what should happen then when something happens? Well, if someone gets employed, you have to assign a user ID. You have to create an email address. You have to define whether this person is going to have access to certain buildings, to certain rooms, to certain facilities. And probably the person should get a telephone also. And there are a number of other things that should happen when this person gets employed. And there are also a number of things that should happen when the person isn't employed anymore. And what should happen then might differ if the person is sacked, or if he has changed jobs within the organization, or if he has gone to another organization. Like if this person has a role and is able to do things, then you probably want to cut him off completely if he gets sacked. Now this is business logic. This is something that has to be defined within every university. And I'm sure it's not at your university. It's not defined. this is normally sort of just happening. And we're working with that. And one of the things that we actually experience is that this has been going on for so long time, so it's such of a lore. It's how things are done, but it's not written down somewhere. So translating this into business logic is a problem. But some of the logic is personal. It's not about the business as such, it's about the person who are within the organization. Like a teacher wants to know when the library buys a book. Well, even if we are sort of, all of us IT people using computers, so if the library buys a book, it might not be that interesting for us. But there are persons at the university who are, their whole life is books. So whether a book is bought by the university or not is extremely important for them. And of course, they want to know if something happens within their area of expertise. So they should be able to specify what that is and to get the information then, depending on things happening within that area. And we have a problem in Sweden. I guess there might be other countries who have the same problem. The funding from the government depends on the number of students that manages to take their grades. So, if the department doesn't enter the grades into the system, the university doesn't get paid. And there is a period within which they have to add the grades. If they don't do that, the money is lost. And how do you get departments to do that? Well, not by telling them to do it, because that's not good enough. I mean, there is no pressure for that. You don't have any pressure for telling them that. So what we're going a roundabout way. We are making the students aware whether their grades are added or not. And they want their grades because if they don't get them, they don't get the loans for the government which students in Sweden can get. So we get pressure from the students on the departments, which means that the university gets the money. Actually, it's a very good way. So anyway, what we needed was to be able to send information about things that happened. Events is sort of the name we are using. Something has happened within one place and we want to send it to another place. So we needed a tool to route the information, the event information, from sources to sinks. But in order for getting this to work, we needed to express the event information in a common way. We needed a syntax which we could use. And the syntax has to be very versatile. And we would like it to have a lean representation. I mean, a syntax being versatile, that's XML. But if you want a lean representation, that's not XML. So, but the nice things with RDF, which comes from the Semantic Web, and that's the connection, I guess, to the Semantic Web here, is that it has a representation which is called n-triples, which is rather lean. It has some other features which is also nice in our context, so that's what we chose, RDF. It's a general purpose language for representing information. And you have this serialization format, which is the n-triples, which is very good for machine processing. And you don't know why this is important yet, but it turned out that there is a one-to-one matching between an n-triple representation and the S expressions. And how many knows what an S expression is? 1, 2. Yes. S expressions, this doesn't show S expressions, so maybe you should go back first. S expressions is something that Rivest from RSA started to talk about like 10 years ago or something like that, to be used in authorization instances. And it has been also used in IETF within a group which is called Spooky, simple public key infrastructure because they thought the PKI was too complex, so they wanted to try something, another different route. Anyway, we picked this up, these S expressions, like 5 years ago, and started to build the authorization server, which is based on S expressions. So we had that. And it's a policy engine. It can compare, sort of, it has a number of rules expressed in S expressions, and you can have a statement as an S expression. And then you can say, is the statement sort of part of the rules? In normal cases, you would say, is this person allowed to do this? And the rule says yes or no. But you can use it for other things too, which we did at this case, in this case. So anyway, this is an n-triple representation of an event. In this case, it's a person who comes to the university. You see the source, the first line up there where it says Primula. That's the HR system, the human resource system at the university. It's the payroll system. And this is the event number 6,648. Well, it's a random number. And it's a person, and you have some information about the person. You have the national identification number. This is because the human resource system uses that as the unique identifier of persons. It's not something you want to use within the database, in sort of the directory for the university, because national identification number changes. It's not stable. So we want something which is stable. But anyway, since the human resource system knows it by that name, we have to use it. And then you have a given name and surname and so forth. This is a simple structure. It's every line is a triple. You have an object, you have a predicate, and you have a subject. Actually, it's the other way around. It's a subject, predicate, object. But anyway, it's a very simple structure. So now we have a syntax. So what about routing? So we need to have these RDFs compared to rules that says, well, if the RDF looks like this, it should go to that place. So this is where the S expressions comes in. So we translate the RDFs into S expressions, compare them to the rules we have in our policy engine, and out comes the recipients of that RDF. So, and this is, the next page is for people who have sort of a weak stomach. You can look away. This is, this is what it can look like. The matching rule upstairs on top, which says that if it comes an ad and it's about the person and it's come from this specific source, which is the human resource system, and then you have the return information, which is below, and it says it should use this protocol, and it's XML RPC, and it should send it to that server over there at that port number. And by the way, of the information that originally was in the RDF, strip away everything except for these parts of it. So you want to send on the object identifier, the user ID, the given name, and the surname. You didn't want, in this case, to further to send to the recipient the national identification number. It was stripped out by the router in this case. And a couple of users examples. We have built a meta directory tool based on this. And we are building a subscription system. First, the meta directory tool. You have the routing system in the middle. You have the human resource system. You have the student system, which is called LADOC in Sweden. You have on your right-hand side a directory, an LDAP directory, which is the point of access for external systems, external applications. We have a database, and we had admin graphical user interface to that database. Why do you have a database in this case? Well, you have person that comes in who are employed, and they then may become students. You have person that start off as students and then get employed, and so forth. And when they are not students anymore, the student system says to our meta directory, remove this person. But the person is still employed by the university, students shouldn't be removed. So that kind of logic we have in this database. We also have the situation that a person may have several addresses. That's very common among students. They have their parents' address, they have the address at the city where the university is located, and they may have another address. And we store all of these in this database, but as the active address, we only show one of them in the LDAP directory. And this is sort of the flow that goes through the system. You have sources, and that might be any type of source. Like it can be a database, a SQL database somewhere. And in this case, you have adapters. And the adapters, they take out the event. Either they get the pull or push sort of. The source might push the information out to the adapter. But some of the sources, they don't do that. So you have to pull the information out from them. That's the work of the adapter, to receive the event information. And then it does this transformation from the internal representation in the source to the RDFs. It does a couple of other things like character sets translations and stuff like that. And then it places it in a directory system, a mail directory system. The UDS router picks it up from there, looks at and uses the router to decide where it should go, and off it goes into a directory again. Each event is a file, which is placed in this directory. And then the receiver of this picks it up from the directory and uses whatever means it has to push it into the receiver. It could be an LDAP directory, in which case it would be, so the adapter would be an LDAP client. We have implemented this. It's written the routing system, except from the policy engine which we had already, but the rest of it is written written Python. A couple of the adapters are written Perl. But the things that sort of the interfaces to the adapters is like they have to be able to place a file in a directory containing an event. I mean, you could do that in any type of language. It's not a difficult operation. Why we used Python is that when I started writing this software, I'm an old C programmer. I wanted to use some other language, and I thought, why not use Python? It sounded like a cool language. So I wrote it in Python. And it's very neat. This is, right, so this is in operation. First stage of it is in operation. We have the person information in there. Now, when I say employees and students here, it's not completely true because that's not, well, it's this, the employees and the students, but that's not all the person that's working at the university. Because we also have persons working at the university who isn't employed by the university. And I'm sure there are persons who are employed by the university but not working for the university, but that's another thing. So we have just started the second stage, which is that we are going to insert more things like roles, like groups, like courses, information about courses. And we also want to bring in guests. This is going to be the source for managing who has access to sort of any kind of application on the university, whether they're allowed to enter a room, whether they're allowed to use our mail server, whether they are allowed to use our network or anything like that. This is the system going to decide whether it's allowed or not. So any person who should have access to something has to be in there, which means that we have to have a guest account and that forth. And we're working on administrative GUI. That's an ongoing story. It's never going to end. and other sources and so forth. As the last example, then, the subscription service. So any library, they buy a book, they start subscribing to journals, they get information services and so forth. And they have, today anyway, no means of getting that information into the researchers, to the teachers and so forth. So we are going to put up this subscription service where the teachers and researchers can go to a web page and say, I want to know when things happen within these areas. And then they sort of click on a couple of these different areas. And then they can get, if they want, either mail, fax, SMS, or they can subscribe to RSS, publication of the events and so forth. Doesn't really matter. We could do other things too. So, this is my last page. We have a first implementation. It has filled the role it was meant to fill. We're not done. There are lots of other stuff. And I don't know how in time, how many minutes do you have? Good, plenty of time. So, okay. So, and we believe I've proven that the idea is sound. It actually works, and it fills a void. I don't know any other system that does this. A couple of the, so when I now have some time, maybe we can do questions later. One of the things we're actually looking at right now is that when it comes to business logic, you can use UML, at least in some cases, to express business logic. There is a way, if you're using a restricted system UML, you actually can translate that into RDF, which means that if we write our sort of description of our business logic into UML, we can use that to fill our routing system with the information on sort of which information should go where. But that's a bit in the future, I guess. Another thing, when you have RDF, there are RDF databases, specially built for RDF graphs, where you have these query languages. So, and that's also quite neat. You can actually sort of put a query to the RDF database and get out sort of a subset of all the events that has happened since we started this system. And that's very useful if you want to, for instance, have a new sink, a new receiver of this information, and you want to bootstrap it. Then you can use these things to sort of pick out the information that should know about, and you bootstrap that into the system. Anyone understand anything? Oh, good. Nothing. Wake up. So, questions?
Who has questions?
Or should we do the other first?
Ah, there's one. Yeah. And the button.
I would like to ask you, what's the user interface between the system and the user, actual user, a worker of the university? Is it the web page, or is it some GUI program for Windows, or I don't know? It's Tomcat based. So it's the web server and the web pages. Is it or why the Python was used, not, I don't know, like PHP or something? Is there any specific reason?
No, just because of fun of it. I wanted to see if I could program. I knew I could program in C. I wanted to see if I could do some other programming language. That's the only reason.
Thank you.
More questions? Well, then I have a question. I mean, you mentioned that you basically somehow acquired, I don't ask why, the business logic of the university, or the rule set how to process certain workflows, certain operations. I mean, if your system works completely, you should have a more or less complete set of business processing instructions and business processing authorizations in your system. Have you ever thought of, first of all, analyzing them and visualizing them to show, first of all, they are, for instance, deadlock free, and second, to show to your president, this is how your university works?
Absolutely. I mean, we're not there yet. We don't have the full business logic there yet. We know how to bring it in, sort of, and we are working on finding the information. But for sure, I would like to do that kind of things. Like you have this, you're allowed to delegate, like the things you can do, you're allowed to delegate to other people. Like the head of the department can delegate to someone else to do stuff. And really, when we asked this question first to the board of the university, you could say, and how, if this other person, is that person also allowed to delegate? Yes, they said. And how many steps? Infinite steps, they said. And to who? Well, anyone who is employed by the university. So, means that the head of a department can delegate to someone who delegates to another one, who delegates to the third one, at another department, or some obscure sort of place within the university. And I'm sure they would like to know that. And especially if someone then sort of quits its job and you want to follow the route of the delegation, so you can pull them in again.
Should be interesting to see that.
Yeah.
Are there more questions? Okay, then let's thank the speaker again. Now we turn to our remote guest, Christoph Bassler from presently Derry, Ireland, but I believe you are in Austria in the moment?
That's correct. I'm in our Austrian part of the institute, yeah.
So you're basically everywhere. Chris Bassler is probably known to the community. He's have you been involved in the oil project also?
No, that's the American-funded research, so I'm not involved in that.
Yeah, but he has been involved in many parts of the semantic web, and he's now talking about semantic description or semantic definition of web service interfaces, which is, I believe, is of special interest to this community because there are many grid people here, and grid people do offer high-level application services. And well, the floor is yours.
Okay, so the sound is breaking off. Hello?
Hello. Yeah, you ready? So you can start.
I'm ready. Yeah. Okay, the sound was breaking off. Sorry.
Okay. Just go ahead.
Okay, so
first slide is on.
So I'll just keep going. I mean, the sound on my side keeps breaking off right now. So let's see how this goes. Can you understand me? Yeah? Okay. So I'm on the introduction slide. So my title is Semantic Interfaces of Web Services. The next slide gives you the contents. So I go through 4 sections of the presentation. First is about web services in traditional sense. So I give you as a starting point what traditional web services can provide to you today. Then we go in a slight detour through requirements about business-to-business integration. What do I really need from a B2B integration area? And if you would put grid there, then you probably would get a similar set of requirements. and then I return to web services, but in this case semantic web service, so the enrichment of web services with semantic web technology, and then in the end I summarize. Next slide please. If you look at traditional web services, then you find two main technologies. One is WSDL, the web service description language, and one is SOAP, the simple object access protocol. Usually there's a third one mentioned called UDDI, but I'm not talking about this at this presentation, so that's the reason why I'm not showing it in my slide set here. The main idea behind web services as they started a while back is the remote invocation idea. So fundamentally WSDL is a language that describes an interface through operations and messages. We'll later see a concrete example. And then there's an implementation behind the interface by a server. The messages, when you invoke this interface, or the result you're getting back from that interface, that is done through so-called SOAP. And SOAP is nothing else than a network protocol message layout definition that says how the bits look on the message, on the wire once the message is transmitted. So it's not going to be of further interest to us for the rest of the presentation. And both the WSDL and SOAP technology stack works within and across companies. In the grid context, it's also across grid services. The next slide, slide 4, shows an example which we detail out a little bit later down the road. On the left upper green box, you see an invocation of a web service, which is called join strings response is the result, and that's the result of an invocation called join strings, and there are two parameters, TNC2005. These are two instances of two strings. If you follow the black arc, then you see a green SOAP message. So this is representing the encoding of this invocation as a SOAP message. And SOAP is transport of HTTP, so it goes through a company boundary or network. So it's the red line, which represents network or the internet. And then this message is received by the interface of the web service. So the service is called join string service. So the green line is the interface, and the big green box is the implementation of that service. And underneath you see a little WSDL definition that says the response, the join string response, is returned by a function called join strings, and there's a first and a second string provided. So once the SOAP message hits the service, then the strings are joined, and then the result is returned back to the invoking client, which then has the result message in its hands. So that's as simple as that, and then whoever was around long enough is definitely reminded by this about callbar or remote procedure calls or RMI. And from its onset, that simply was initially the idea, because if you look at SOAP, it's an acronym standing for the Simple Object Access Protocol. That's definitely coming out of the object-oriented world. So if you go to slide number 5, then we see a WSDL example, and it's an operational example of what we just talked about. And on that slide you see 4 blocks of text. The first block is defining a whole bunch of namespaces, so definitions can be uniquely told apart. The next block is a definition of a message, and that's the message that is sent as an input parameter to the service. The next block is the join strings response message. That's the message definition for the result. And the fourth block of text here is definition that says there is an operation with an input and output message. So that's defining the interface in an abstract way. And the next slide, slide number 6, shows then how this is bound to a specific protocol and a specific implementation actually. So the upper part of this binds this abstract definition to a SOAP technology stack where messages are sent over HTTP in a remote invocation fashion, synchronous invocation. And the lower part of the box shows how this is bind to a specific implementation. As you can see, there's a localhost HTTP URL given, and that fundamentally says go here if you want to invoke that particular service. So that's really where the implementation happens. So all of these 2 pages are enough, so to speak, to define the interface and to point to the implementation of that interface. From a client side, slide number 7, from a client side, here is 2 columns of text. The left side is doing a bunch of imports in the Java language. That's using a particular implementation of web service invocation framework, WSIF, WSFIF from Apache. And that's how you would kind of write down a client in its abstract form. And all this is necessary to bind the appropriate Java binaries and libraries, sorry. But then on the right side you see in bold the client.WSIF client invocation. And that's really where the invocation happens, and that function is detailed out on the next slide, which is slide number 8. And in slide number 8 you see the definition of that function that fundamentally builds up the 2 messages, builds up the input and output messages, and then finally does the operation. So on the lower right side you see the execute request response operation, and there you see the input, and this is where really then the messages are sent over the wire and are kind of taken back as a result, whatever the result message is all about. So this is how you kind of do this implementation, and that invocation then is operational. So this is an operational example that works, and that's as easy as that, in quotes, to make a remote invocation. So that's the technology as it's today. And if you go to slide number 9, then I'll start investigating the situation a little bit by looking first at the communication paradigm. And this communication paradigm is clearly a client-server paradigm. First of all, we only define the interface of the server. We're not kind of defining the interface of a client. So the client invocation interface is undefined. And the relevant observation is here that a client, of course, can invoke a server, but the server in turn can invoke another server. So all of a sudden a server becomes a client, and only the invocation side is described, not the other side, which is going to be a problem, as we're going to see later on. And as an example, what would be the client invocation interface? Well, that would be those invocations that the client issues that are externally visible. So in our example, the execute request response operation would be the one that you could define the client interface, but it's not done in web services today. So if you go to slide number 10, you see when we look at the service definition, then in the web service world, right now only the interface of a web service is defined. The definition itself is non-existent. So there is no internal composition possible, so you can't define what the service does internally. You can't say that the service is elementary in the sense that there's only one operation that operates in isolation, or that there are only 2 operations, something like that. And you cannot define any non-functional properties. You cannot say really if a service should be free or service should always return within a certain time limit, it should be secure, any of these non-functional properties. So it's a very, very simple, very basic mechanism. If you go to slide number 11, if you look at the data we can send across, then WSTL only accepts definition XML schema. Anything that you need beyond XML schema cannot be defined by the web service. So if, like in the B2B world or in the grid world, if you have complex data structures that need constraints beyond what XML schema can provide to you, then you won't be able to formally define it, as web services only allow you to do XML schema. So if you look back to our example, then our example was joining 2 strings, and the result was giving back to us. But then of course the question arises, what does it precisely mean to join 2 strings? Does it mean that there's a string and then there's the blank and then there comes the second? Or does it mean there's the first string, then there's the bar, and then there's the second string? Or does it mean the 2 strings are concatenated without any separator in between? We don't know. We don't know because the web service interface does not allow us to define what it means by joining 2 strings. And if you really want to know this, if you're really interested in that, then we have to look into the definition, or the implementation actually, and that's done on slide number 12. Right, there's the implementation of the web service in Java code, and here you can see this implementation was chosen to concatenate the 2 strings with a bar in between. So only if you look in the implementation you understand what the web service does, which clearly indicates to us that the interface definition language is not powerful enough to even describe simple scenarios. If you go to slide number 13, then I have here the intermediate conclusion. which fundamentally is the communication paradigm in the traditional web service world is clearly client-server. The service definition defines only the interface of individual functions, not complex scenarios, and the data semantics is clearly limited by XML schema. So that's what it is. That's what you buy today if you buy technology that implements web services, and that's what you be told is solving the integration problem. And I'm pretty sure the grid community is going to be told this too pretty soon, sooner or later. But then let's look into the real requirements of the real world to some extent. So let's go to slide number 14, which then introduces the next section, which is the business-to-business integration world. So this is a world where really you have to make integration work through many application systems that exist. So to give you an example, a bigger company like the Boeing company building airplanes in Seattle, they have thousands of applications that have to work together. They have to be integrated, and their integration is quite complex. So if you would like to use web services, then the technology is not adequate to express the integration needs. So slide 15 shows the general layout of B2B integration. It shows you two companies, blue boxes, company 1 and 2. In this area, they are also called trading partners. And then there's the internet in between, for an example. There are other networks out there. There is Swift network from the banking industry, and then there is value-added networks for the supply chain industry. But let's assume the internet for the remainder of the presentation. Then usually what happens if you go to slide number 16, what happens is the trading partners send electronic messages to each other in order to conduct their business. So for example, in this example that I have here, a purchase order is sent from company 1 to company 2, and company 2 then does some internal computation and checking of goods and supply chain operations to figure out if they really can ship the goods that are requested at the timeline requested, the price requested, and let's assume things go well, they send back a purchase order acknowledgement. So company 2 returns then to company 1 a purchase order acknowledgement. So what you can see here is that while there are messages going back and forth between the companies, it's more or less like a conversation. One company sends a message, another one returns a message, and this might be a quite complex process, not as easy, not as simple as displayed here. And I have some more complex ones to show you later on. If you go to slide 17, then we see the internals of these companies. So fundamentally, once a purchase order is sent, then the difficult part was already done. Before you can send a purchase order across networks, you have to first extract the data from an application system that really kind of has the sign-off taken place and acknowledged, and then only you can send it. And once it's sent across the network to company 2, then it has to be fed into the application system for further processing, like for example determining if the parts are available and the shipping can be done in time. And this application then, just after the computation, sends back the purchase order acknowledgement. It has to be extracted and then is sent over the network and put into the application of company 1. So while there's messages exchanged across the internet, of course, within these companies, these messages are generated and consumed, of course. So in slide 18, you see that I put in another application called integration server. That's middleware that allows the extraction and sending of messages. And as you can see, I also added additional messages, how the flow really works. So in addition to the messages between the companies over the network, you also have the messages within the companies between the applications and the software that does the exchange. So on the far left side in the company 1, you have a purchase order prime being extracted, but then the purchase order is sent across. So the problem here is that the data formats, the data models in these applications, as well as on the standards used for the message exchange over networks, those data formats are different from each other. So this integration server has to do data transformation or data migration in order to ensure that the formats are obeyed while preserving these precise semantics. The same happens once the purchase order is received from company 2. It might have to be transformed into PO double prime in order to get into the application in the data format this application understands. So as you can see, from one application to the other application, the data is transformed 2 times. So the data is represented 3 different ways along the way. So data transformation is definitely an important requirement. If you go to slide number 19, then we have a slightly more complicated scenario where after the purchase order processing, also shipment information and invoicing is happening. So here you can see that there are more messages going on across the network between the trading partners, but also within the trading partner one, where all of a sudden more applications come into play that not only do the purchase ordering, but also the invoice processing and the shipment management. And if you go to slide 20, then another application is added that maybe does the payment processing. So if you would really write down this example in all its glory details to a really real example, then we probably would touch many more applications and had many more trading partners involved in this overall process. So as you can see, there's not just a back and forth conversation between two partners. There's a lot of conversations that are chained together that all have to work in lockstep in order to achieve a consistent business semantics. So if you go to slide 21, then we go through the same questions again that we did before with web services. And fundamentally, one observation we can have is that there is a conversation going on between trading partners, and not really a client-server behavior. And the difference is that in a conversation, both partners know about each other and know each other's interface, so they can communicate the right messages at the right time over time. And one possible representation of this are processes, interface processes, fundamentally, that show how an interface looks like from its progression once messages are sent back and forth. If you go to slide 22, then I just removed the network from that presentation, and fundamentally this shows that when one company sends a message, the other one must receive it. So these are the arrows that go horizontally, but on the vertical arrows you see that the messages that are sent and received by a particular partner are to be ordered too. So as the shipment is received, then the next thing that has to happen is the sending of the invoice. And fundamentally, to represent that, you have to be able to say something like receive shipment, send invoice, and make sure that the sending of the invoice is after the receipt of the shipment. So these processes fundamentally allow to define not only that messages are going back and forth, but also the execution order. And of course, the execution order can be conditional, can be loops, and all sorts of complicated control flow structures. So on slide 23, I have the argument why it's necessary that both partners represent their interfaces, not just the server and the client is not represented. Because if you look at the discovery process, when you are a client and you look for a provider, fundamentally you're looking for all these companies that can provide a certain good to you. But then if you put yourself into the shoes of the provider, then you can ask the opposite question. Search me for clients that might want to buy my goods. So all of a sudden the provider searches for clients, and in order to search for clients, it needs to know the interface of the client to make the proper selection. So as a consequence, you need the interface of both, not just from a conversation paradigm, but also from making proper discovery from all partners' viewpoint. If you go to slide 24, then this example tries to show that you have a complex chain of invocation relationships across a number of companies, not just binary relationships between. So for example, if you look at company number 2, then we can see that it's being contacted by company 1, but it internally contacts company 3 and 4. So it internally somehow it needs to be able to specify that company 3 and 4 has to be contacted. Maybe there's an order, maybe there's in parallel, we don't know, but the company internally has to provide a logic in order to execute all of this that go beyond the interfaces, of course. So let's look in detail in company 2, which is done on slide 25. So here we can see that the company 2 has one interface to company 1 on the left side, but it has a different interface to company 3 or 4 on the right side. So fundamentally, it talks to its clients, so to speak, through one interface, and it talks to its providers through a different interface. So there are two interfaces the company 2 has to worry about. The one which it is contacted by, so like the A contacts company 2 to message A, and then it returns message B and so on. But it internally might require a supplier to help, and so it has to send out E and maybe get a response F back. So from company's 2 viewpoint, it has two interfaces, and these two interfaces have different names to distinguish them. The left interface is usually called the choreography, and I'll go later in the terminology, but you fundamentally have a difference between the contacting interface and the interface you are contacting others. So if you go to slide number 26, we have a brief discussion on data semantics. Documents are complex, and there are many constraints within documents on the values in the documents that go beyond what you can do with XML schema. Not just in the business world, but also in the scientific world, which certainly the grid people appreciate. And as we have seen earlier, the mediation is necessary to translate from one representation to another one in order to cross the boundaries of the definitions of the company. We have an application implemented, let's say in SAP ERP system. It has certainly a different representation than a standard that Message Exchange uses, like EDI. So the semantic complexity comes in through concepts, abstractions, consistency rules, correlations, and all these kind of necessary elements that are beyond what XML schema can provide. So on slide 27, I put together these observations fundamentally as a table, as a comparison, and then we can see that web services have a communication paradigm, the client-server approach, whereby B2B has the conversation as a requirement. Web services have only the service interface as their interest, whereby B2B has not only the interface but also the composition. Composition meaning the order in which operations on the interface are executed. And on the data semantic side, web services give you XML schema, but you need more. You need expressiveness that goes beyond XML schema. So from this comparison, it becomes clear that while web services kind of say they provide all of what you need, in reality they don't. And the difference is usually an enormous amount of additional programming that has to take place in order to make this implementation work. So as a conclusion on slide 28, web services cannot live up to B2B integration requirements due to a naive conceptual model regarding communication paradigm, service definition, and data semantics. And if we look at the grid world, I'm sure we could have the same discussion there. If you look at the complex grid scenario, especially if you have long-running grid services that run more than instantaneous time, or where data are rather complex in their structure. So at this point, having done the comparison, having done the requirements analysis, I go to slide 29, which then gives us the entry to the semantic web services piece, and slide 30 then gives the vision of semantic web services and semantic web service technology. Fundamentally, the idea of semantic web services is to have automated discovery, combination, invocation of web services. So the discovery fundamentally means, given for a certain processing, have the environment go out and find services for me that are adequate. So if I want to buy a book, then the service comes back and says these are booksellers. Or in the B2B world, if you go to production lines, and if I'm a car manufacturer, then I say, well, I need light bulbs, and then the system comes back with services that provide me light bulbs, not only in the quality I need, but also in the price, as well as in the delivery time. Combination of web services is the composition. So if you have many out there, and you need many of them work together for you, so you can achieve your goal, then you have to combine them in such a way that they're making sense. And it would be nice, of course, to have this automated. And then the invocation, of course, once you have all this in place, once you have discovered what you need, once you have combined the services, then of course you want to make the environment, make the invocations and really do the business for you. And all this is the web service technology really scalable and mature. There's no way around that. And that's the goal that we have when we work on the semantic web services through our European Union projects as well as the working groups, and I have a web pointer for you later on. So I would like to skip 2 slides and go directly to slide 33. And in that slide is a high-level representation of the conceptual model that we have that allows you to address all the requirements that I just outlined in the B2B field. So the 4 main elements are ontologies, goal repositories, web services, and mediators. That's all you need on a high level in order to define integration, and later on I'll show you a language that allows you to write these down. Ontologies are formal languages, and W3C through OWL has made a web ontology language prominent that allows you to write down complex data structures through means of concepts and relationships, as well as attributes, constraints, axioms, and all sorts of other constructs. And these ontologies allow you to write down complex data structures that go beyond XML schema. And once you have written down these ontologies, then it also allows you to do some reasoning, so inferring facts from the structures that are not explicitly represented. So ontologies are our means to write down data structures, be they as complex as they are. Then goal repositories are elements where I can write down an intent, what I want to achieve, like I want to achieve the purchase of a certain set of light bulbs, or my intent is to buy a book. And these goals then allow you to match to web services that can fulfill these goals. So if I state a goal, then the system through that mechanism can provide me with web services that fulfill that goal. And now what I can do is I can decouple the precise match to a goal-oriented match, allowing me to compose web services. And web services themselves, of course, have to be described. So here we have a language for the interface definition, especially these processes I mentioned. And finally, we have mediators. And mediators are prescriptive rules, are rule sets that allow you to transform one ontology into another one. And this allows you to overcome the heterogeneity. So if every web service provider out there in the wild web defines its own data model, then every time you contact one, you have to adjust the data structures, and mediators are a means to achieve that. So if you go to slide 34, I put all these elements into a graphic representation that you're to some extent already familiar with from earlier on. So in the middle you see the green box, which is the web service implementation. We have seen this before. And then you have 2 processes, a choreography and orchestration. So choreography on the left side is the process that defines how you contact a web service and how do you get benefit from a web service. So it says, send me a message containing your product definition, I return you a message indicating availability. The orchestration is when a web service in turn contacts another one to fulfill its goals. So, for example, when availability needs to be determined, the web service might not be able to do it by itself, but it might have to contact another one for that, and then it uses orchestration to accomplish that. The data that are communicated through choreography and orchestration are defined by ontologies. When you send a message to a choreography or to an orchestration, you might have to re-represent your messages in a different format to adjust the heterogeneity differences. This is what mediators are for. And then all this together is the web service, and the web service fulfills a certain goal. So this is how this all hangs together. So now if I have a goal, then my web service can tell me what data it needs. If I send the data, it might mediate it to its internal format, and then it does the computation, potentially using other web services through its orchestration. So if you go to the next slide, slide 35, then you see a language that has been developed that reflects directly the conceptual model. So here you see as keywords in the language itself things like web service, capability, ontology, and so on and so forth. So if you go from top to down, first of all, we can introduce namespaces in order to distinguish synonyms, of course, and make certain definitions available. Then all what I'm doing here is defining a web service. That's taken from a document that's available to you on the website vismo.org. It's in the last line, there you have the website. So this web service implements a book ticket web service. We can book tickets. It imports a certain ontology, so there might be already a data definition out there, which is the trip reservation ontology. So you might just use that because it almost does the job for you, so you import it. Then you say that this web service implements a certain capability. So by stating the fact that the capability is a book ticket capability, everybody who wants to book a ticket might get this web service returned, so you don't have to search for it individually. And then of course there's an interface, the book ticket interface. Now that interface is outlined a little bit in more detail below. So the interface, book ticket interface, also imports an ontology because interfaces, as we have seen, need to send and receive messages. There's a choreography and there's an orchestration that outlines how these interfaces look like in detail, those processes, and so on and so on. So there's a Vismo primer, this deliverable 3.1 from a working group at vismo.org that shows you this example in glory detail, and it shows you how you can define all these elements of web service semantically. So fundamentally, if you go to next slide 36, you see that all the requirements are covered. Fundamentally, the communication paradigm is cooperative in conversations because you have choreographies and orchestrations working together as conversations. You have the service definition as processes, so you can really say what happens in which order, which allows you to understand these web services. And from a data semantics viewpoint, you not only can define data semantically, but you can also mediate between the two. Slide 37 briefly indicates that we have a reference implementation of all of this available as public source, where you can define your web services using this language. You can feed it into a box called Vismix. This is our interpreter, and this interpreter then can invoke and execute web services. Slide 38 shows you the detailed architecture, and while I don't want to explain every single detail, but if I would like to point out certain elements of it. So for example, if you look at the right side of the architecture, you see a box called service providers. You have 3 web services. So these are made available to the architecture, so meaning you can invoke them. And then right underneath the box called Vismix management on the right side, you have a box called orchestration, you have another component called choreography, you have another one called process mediator. So all this functionality we talked about is implemented as components in this architecture, meaning that this architecture can execute these functionalities individually. Slide 39 shows you in a graphical representation 3 working groups that define this semantic web service model, language and execution environment. And if you just remember the vismo.org website, then from there you can find all what's available and who's working on it. It's not just dairy, it's like 2-3 European Union projects that together define all of this. So if we sum up and we go directly to slide 42, then fundamentally we can see after this discussion that web services are a very simple and naive conceptual model following the RPC paradigm, whereby through the B2B discussion we have clearly seen a lot more expressive environment. So we need something like semantic web services that gives you an expressive conceptual model, gives you the support of semantic interfaces, and through that then allows you to cover the B2B requirements and any other requirements integration like enterprise application integration or grid integration. Thank you very much.
Thank you very much, Chris. Can you hear me?
Yeah.
Yeah, okay. So, other questions on this heavyweight talk? Very rich of topics. No questions? So then I have a question more on strategy or on the working groups. How does your work relate to the OWLS semantic web service description?
There are two ways to relate it. One way, purely from a scientific viewpoint, that's competitive work, but it's not where we stopped. 3 years ago, we jointly with the OLS community founded an organization called SWISI, the Semantic Web Service Initiative. And in this initiative, we got together and discussed for almost 2.5 years now how we take the best from all the approaches to get to a one common model for semantic web services. So take the advantages of all these approaches and combine them into one approach. And this, along the way, led to a few member submissions to W3C. So OLS has a member submission, we have one, and SWISI actually has a member submission. So all these submissions then fundamentally show the differences as well as the commonalities. And I'm in Innsbruck right now, and tomorrow and the day after tomorrow, there is the W3C workshop on semantic web services going on that has as goal to exactly that, to get all the parties on the table and hopefully then start a working group in W3C that follows the W3C rules to kind of work on a standard. More or less like OWL came into existence by putting a US and European competitive proposal together and building a better language out of it. So the same we're doing right now here in Innsbruck.
Are there more questions? So, then let's thank you very much again and good luck for your efforts on standardization of this different approaches.
Thank you very much. Thank you.